Good morning, everyone. My name is Daniel Wood. I'm the Managing Director Maritime Europe and West Africa for ABL. Our briefing this morning is accredited to the Chartered Insurance Institute, and delegates can claim up to 1 hour CPD for your participation. We will therefore keep a record of those of you in the room today and those of you logging in online. If you haven't done so already, please make sure you sign in with the team on the desk outside after this briefing in order to be able to receive your follow-up email and CPD certification. Just a quick reminder today as well, we will be ending the webinar portion of the briefing after the technical presentation, and the marine casualty case reports moving forward will only be presented in person. Of course, we are happy to discuss with anyone who would like more information on them post-briefing, and to look how we can make the data available to you. So please do come and see us afterwards. I'm delighted to introduce our technical presenters today. Andre Vidal is a marine consultant and head of ABL's team in Portugal. He brings extensive experience from his background as a fleet manager and class surveyor, particularly across the Mediterranean region. Over his career, Andre has led a wide range of surveys, including hull and machinery damage assessments, condition and pre-purchase surveys, as well as docking and statutory inspections. With his deep technical knowledge of vessel systems and propulsion design, he's well placed to deliver today's presentation on propulsion shafting alignment, addressing risks in design and survey. And delivering the case reports, we have Stanley Pritchard, mechanical engineer on the ABL Group Engineering Development Program. He's currently working for ABL, and we are equally pleased to have him return this month to present our marine casualty data. Usual caveats apply, Chatham House rules, and the information contained in these presentations and any opinions or comments expressed are those of the presenters and not necessarily those of ABL. At the end of today's briefing, can we please ask everyone just to take 3 minutes out of your time to complete the online survey? This is really critical for us. It's a crucial element of our CPD accredited status. We want to be able to keep offering that opportunity to you to get 1 hour CPD point per briefing. So please, can you complete a form? It also means we can actively look at how we can improve these briefings to match your requirements and needs. Thank you. You can download it via the QR code. We will also send it out in the follow-up email. As these briefings are accredited, a very important criteria of this is to run through our learning objectives for today. So in terms of what you will learn, you'll gain an understanding of the key factors influencing propulsion design alignment. You'll be able to describe the consequences of misalignment from bearing damage to high-value repair cases. You'll be able to calculate methods and installation practices to achieve accurate shaft alignment. You'll be able to review practical guidance for alignment surveys and monitoring during a vessel's operational life. And finally, you will understand takeaway lessons learned from real case studies to support safer and more reliable ship operations. We will go over these again at the end of the presentation. Happy to report that last month, Jason Bennett, our Marine Director, and Claire Smith, GSS Case Manager, who's in the room today, completed an incredible 13,000 feet skydive in support of Haven House Children's Hospice. A massive thank you to everyone who's donated so far. Your support has made a huge difference. The challenge isn't over yet. This month, Steve McCarthy, our Associate Director of Marine Services, also in the room today, will also be taking the leap. And there's still time to support ABL London through the QR code on the screen. Thank you. And now on to Andre Vidal for his presentation. Thank you.
Morning, everyone, here and online. I'll be talking about propulsion shafting alignment. Most of the shafting alignment issues are related with non-alignment. I mean, if we have a vessel perfectly aligned on resting on blocks, when the vessel goes to the sea and floats, sometimes it doesn't mean it's aligned, and we'll see that in the future, in a few minutes. The content will have some background, engine bearing damages, which are the most common damages we have. The factors that contributing to these alignment changes are mainly two: thermal rise and hull deflections. Point 4, the alignment calculations mainly done by engine makers and class societies have a number of engine bearings in calculation and the equivalent crankshaft model. This is just, we'll pass this just to have an idea what they do. Point 5, the engine installation, guidance for propulsion shafting alignment, and finally we'll have some pictures and with some inspected damages for the last years. So the background of this: why is the shafting alignment becoming a major concern? Engine bearing loads tend to increase due to increase of the engine combustion pressure. So the bigger we have, the bigger engines we have with higher combustion pressure, the more pressure we have on the bearings. The majority of the cases we have are with number 1 and number 2, those two red triangles. You can see here, just for your guidance, you have the crankshaft that's inside the engine. Those two red triangles is the thrust bearing, and then you have the flywheel. That's the first equipment that you see outside the engine, the main engine, and then the intermediate shaft, eventually a tail shaft. Engine manufacturers, Wärtsilä, Burmester, are offering instructions concerning engine alignment based on engine deflections. We can see here the same drawing, but now with the tail shaft and the propeller. You see the thrust collar, and those number 1 and number 2 are where we see more damage, especially in MAN engines. 2 pictures. Typically, we have the engine bearing upper metal and the lower metal. On the edges is where we see metal peeling and worn out. This is typically two-stroke engines. Engine bearing damage positions, the Wärtsilä for the eldest used to be called Sulzer. Now it's Wärtsilä Group. And there where you see MAN, now it has another name, is Evalance, but we still have in the plates, the ID plates of the engines, it still is there, MAN. So, but these two major manufacturers, and then there's a third one, Mitsubishi. MHI is Mitsubishi Heavy Industries. But they tend to differ on the type of damages. Wärtsilä engines have damages on the middle, more or less, bearing number 5, number 6, depending on the number of units. And Evalance and Mitsubishi, they have further on the back. We'll give 2 examples, Ship A and Ship B. They are sister vessels, product carriers, with 28,000 gross tonnage, 13,000 horsepower. It's a 2-stroke engine where after 1 year of service, an engine bearing damage occurred. And on the sister vessel also same damage occurred. So you can see that it's not it's a recurrent thing from time to time that may happen. Bearing damages or bearing loads. Engine bearing damages, number 1, 2, 3, 4 bearings. Just for your reference, normally the numbers of units are count from aft to forward. Number 1 is closer to the flywheel, and the last number will be closer to the vibration damper, forward part of the engine. And so number 1, 2, 3, 4, lower metal damages, specifically on number 2 and 3. Melting on white metal was seen. Bearing loads, you can see that regardless of engine being cold or hot, in ballast conditions, we've seen bearings loaded. And on number 2, when the vessel is not in ballast but fully loaded, you see number 2 unloaded. Again, for your reference, this loaded and unloaded means to measure how much load is there on the bearing. They put an hydraulic jack, put some pressure on the hydraulic jack, and soon as the caliper, the smallest caliper, that it's usually 0.05 millimeters, enter, that's the pressure, that's the load that is on that bearing. So now you can already understand that there's a difference when the vessel is in ballast or loaded. So number 2 bearing, the first after the thrust collar is becoming unloaded with no load when the vessel changes from ballast to laden condition. That also can happen on the intermediate shaft. Regardless of the vessel being cold or hot, the intermediate shaft might be, it's unloaded, and while the number 2 engine bearing is also unloaded. Now, to distribute bearing loads uniformly, slope alignment is employed. What does it mean? The propeller, it's a very big and very heavy equipment. And as you can see, and as you know, it's hanged there on the edge of the tail shaft. So anytime you have the propeller hanged there, there is a tendency for the tail shaft to bend. There's a bending moment created there due to the weight of the propeller. And so the way to reduce that load on the slope boring is to create an offset on the main bearings. The lowest, or to a certain point, the lowest offset possible on the crankshaft, the lowest edge loading you will have on the stern tube bearing aft part. Edge loading, okay? Is this clear? So after this, we will have another problem, which is the temperature rise. As you know, all elements will have a temperature rise, and the engine, it's made of steel, will have it too. When the engine is cooled, it will have a certain offset there, a certain height in terms of height for the baseline of the engine. And when the engine gets hot, it goes up, obviously. And that influences the alignment too. You can see here as an example, the same example before, the ship A when the engine was cold. It's that green line over there. It had an offset of 1.4 millimeters. And when the engine gets hotter, that offset diminishes 0.24 millimeters. So the engine goes up a bit. That also, as the engine, as the crankshaft increases or goes up, also there are bearing loads different from the beginning. Aft, forward of the stern tube, intermediate shaft. You can see that the intermediate shaft, in this case, got unloaded completely. So when the engine was hot, just the fact, I'm talking about this, you can see the, no, you cannot see. But I'm talking about that in the middle, negative bearing load. As you see, the fact that it's down means that the intermediate shaft bearing, it's supported on the upper part, not on the lower part. So if there is any damage, it's likely to be on the upper side of the bearing. While on the engine side, also happens on the number two. Number two is, you can see that it's crucial for the engine alignment. And how it changes in terms of loading. Well, when the vessel is in light ballast condition, the engine room is very heavy, as you know. Main engines may weigh hundreds of tons. And so there's a natural sagging of the engine room side, while the cargo side has a hogging. When the vessel is loaded, it happens the opposite. There is a sagging part on the cargo side, and the engine room gets hogged. So again, you can see that's a second factor. First was the thermal rise. Now we have the cargo condition, ballast or cargo, may influence also the shafting alignment. How much can it influence? In light condition, let's assume that's the condition of the shaft. And then when the full load, of the vessel, then we have bearing damages due to changes in loading conditions, have a general tendency that the aftmost bearing, one is overloaded, and the second aftmost bearing is unloaded, or with less load at least. So we might think that the vessel, it's a very stick beam, but actually is elastic. Every time we put load on the put cargo or put ballast, the shaft also fluctuates, also changes condition. How much does it change? Engine room deflections. There are two possible approaches for estimation of engine room deflections. One is finite elements analysis, which is an academic, it's a theoretical approach. And the other one is measuring actually in the engine room in sister vessels, sister ships. We can see here, assuming engine room spans from 21 to 37 meters, which is more or less the engine room sizes from aft bulkhead to the forward bulkhead. And we can see in our example that in ballast condition, it was 2 millimeters. But with the full load, the hogging could reach 6 millimeters. This is a huge, 6 millimeters might look very small, but when in terms of bearings and alignments, it's a huge number. So the construction and the design has to consider these deflections. Now, points of calculation. This is typically done by engine makers and also class societies, but they calculate based on the number of bearings. The biggest the number of bearings, the more complicated it becomes. For your reference, on a tanker, it's usually the engines has 6 to 8, 6 to 9 units, but on container carriers, they might reach 14 units. And so it's a huge, it's an engine very, with a huge length, it might be 30 meters, and it becomes quite a big challenge. And so in theory, what they do is they make an equivalent crankshaft model. So this is a typical crankshaft. Crank journals are the main bearings, and the crank pin is there. And so it is calculated for a straight shaft to be has the same to be equivalent in all matters. On these 7 cylinders engines, typically on a 7-cylinder engine, we have 9 bearings. So we have the 7 units plus 1, and then we have the number 9, which is before, or number 1 in this case, which is before the truss collar. And so in 9 bearings, we have to calculate the bearings load, and the more bearings are calculated, the more accuracy we get. If we calculate from 1 to 9, put all together, we have a tendency to be more close to reality than when we calculate with engines with less cylinder number of cylinders. Engine manufacturers are providing the diameter of the shaft equivalent to the crankshaft for each type of their engines. Just for reference, the equivalent in this ship A is 63%. So the diameter of the shaft, it becomes smaller. It doesn't matter on the stern tube. As you see, it's exactly the same because it's solid. If there is no CPP, the shaft is solid. So the bearings load and the model is exactly the same. It changes only inside the engine. Engine manufacturers are suggesting engine installation with pre-sagging alignment. As you can see, all these figures, this table has all the figures with a minus. That means sagging is like this. And if you can see the engine type, the bigger the engine is, so for your reference, these are the types of engines. S50 means 500 millimeters diameter piston, and 990, S90MC is the MEIN with 900 millimeters piston. It's something like this size. And the bigger the engine and the bigger the number of units, we'll see the sagging has to be bigger also. So engines, not so much, but this is typically the adjustment that it's made when they installed the new engine and the new shaft in place. So, in conclusion, an accurate shafting alignment is very complicated because of the following 3 reasons. Static reasons. The stern tube bearing suffers edge overloading at its aft caused by the propeller overhang. The shafting alignment is affected by the hull deformation. It varies according to the loading condition and the sea condition. The shafting alignment is affected by the thermal expansion in engine operation. So these are static reason. There is a dynamic reason. That is the sea condition actually. So when the vessel is at sea, coping with heavy seas, the vessel is always moving, rolling, and so there are constant bending moments and torsional moments imposed to the shafting system. But these are the ones that we can control. Several precautions against above items are taken as follows. There are some bearings, lignum vitae bearings, where the clearance are bigger than the white metal ones. The clearance to be taken at every dry dock, this is typically taking the clearance or the wear down, and to verify if they are within the acceptable. And what is the acceptable? Assuming NK rules for this type of bearings, it depends also on the shaft diameter. Up to 230 millimeters shaft diameter, it's allowed 6 millimeters clearance. Between 230 and 300, it's 8, and over 300, it's 9.5. If the vessel goes to dry dock and the clearance there, it's like 12 millimeters, it's not acceptable anymore. The bearing has to be removed, tail shaft withdrawn, and replace whatever it's needed to be replaced. Second point, as a precaution, in white metal bearings, the tail shaft wear down, again, has to be checked, has to be measured in every dry dock. And here is not the figure that matters, but the difference from the last dry dock. If the difference is more than 0.3, vessel goes to dry dock typically every three years. And so more than 0.3 means it's been wasted more than 0.1 per year. And that's a red light. Number 3, by removing bolts and nuts between the intermediate shaft and the propeller shaft, coaxiality and gaps of shaft flanges are to be measured. Point 4, in diesel engines, the crank deflection is measured and corrected by adjusting choke liners of the engine seat in permissible range. So what we have access during when the vessel is not in dry dock, chief engineer can measure the crankshaft deflections. It's the only tool he has when the vessel is afloat. And so typically the manholes are open, crankshaft inspection, and they measure how much is the deflection of the crankshaft. And there are limits set by the makers. If the limits are reached, then main bearing has to be dismantled, eventually replaced, and something has to be done. Related cases inspected during the last years, these are only some examples. This is quite old. I think it has, I don't know, 15 years old. It has a CPP. The CPP, it's control pitch propeller. And when you have a control pitch propeller, the control of the pitch propeller is done by an equipment called OD box, oil distribution box. And in this case, you can see temperature rise on the bearing over there and with cracking of the shaft. And this costs less 15 years ago, but it's updated to 800, which I think it's a reasonable number for today. Intermediate shaft bearing worn out. This is quite common and can be only repaired by remetallization or replacement. Some shipyards, they don't do that kind of work. They prefer to put a new bearing if it's available in the market. Sometimes it's difficult to get a new one. Another one, tail shaft scratch and stern tube white metal bearing affected, requiring remetallization, 900. This is a relatively recent case. So in these cases, when we have CPP propellers, the rudder has to come out. So to take the shaft out, as you can see, there's the rudder horn there, rudder stock. So for access, the rudder has to come out. So it increases the costs also. You can see an example there on the left of an intermediate shaft that was found bent. Okay, so although we think that the shaft is huge and big diameter, it can bend. And the cost, and there is no other way to take it out unless we make an access on the hull, because intermediate shaft is an equipment. It's a part of the propulsion shafting that it's inside the engine room, and there is no access possible. So the vessel has to be in dry dock or afloat as it is there, but trimmed forward. They trim the vessel forward, make a hole, and take the shaft out. Again, very costly, 1 million baseline, from 1 million up. Stand tube bearing white metal detached, requiring repairs. Typically, you can see that's the edge of the aft bearing, exactly where the overhang of the propeller is, and the white metal is peeled, so it has to be taken out and repaired. Also, recent case, a vessel that was leaking oil from the CPP system, from the hub, and went to dry dock. Soon as it went to dry dock, you can see from the date, it's very recent. As soon as the vessel went to dry dock, the hub was seen cracked. You see? It's not yet closed, but estimations go to 1.2 million. That's it. Thank you very much for your attention. Last photo is the alignment check. This is an alignment check. It's mounted on the aft part of the stern tube, and it goes all the way to the flywheel. So just for your reference. Any questions?
And does the choice of propeller make a difference? You mentioned there was quite a few CPP propeller cases there. Is there any difference by the choice of the propeller and whether they suffer more from the misalignment?
I have to repeat. The question is if there's a difference between CPP and a fixed pitch propeller on the line. I don't think there is. No, there might be a different numbers on the weight of the propeller, because the fixed propeller has a smaller hub, and a propeller with the CPP typically has more parts and it's a little bit heavier. But I don't think it's a question of numbers. Okay.
Thanks for a very great presentation. With the advent of CII efficiency, propellers are getting bigger because a larger propeller is more efficient. Larger propellers are only heavier, but also has more asymmetric loads. Have you experienced any sort of cases where this has become an issue in sort of modern, very recently built vessels? This would be for the stern tube.
The question would be, I have to repeat it so for the online. The question would be if recent propellers becoming bigger, and how they, if they become bigger, how they are more with more tendency to have problems. That's it. Well, I don't know if they are becoming bigger, to be honest. The propeller is always designed to a certain power. So they are, they are bigger if you have a bigger engine. They are bigger if you need the CPP, because the fact that the hub is big means the efficiency is lower, than a fixed propeller. So I wouldn't say that the propellers are getting bigger. But if we're talking about bigger, on the bigger vessels with a bigger propeller, we have similar problems. I mean, the alignment doesn't, it's not directly related with the fact that the propeller is big or small. It's related with the size of the vessel, with the loading, with the thermal rise, with the deflections. But I wouldn't relate directly with the size of the propeller. That's my experience. Thank you.
Does the speed at which the propeller rotates, like how does that affect things?
Propellers, they tend to rotate. The speed is around between 80, 100, 120 RPMs. When we have two-stroke engines, they are directly connected to the engine. When we have four-stroke engines, because they run at higher speeds, you need a gearbox to reduce that speed to 100. Again, I don't think the speed will influence that much. We're talking about loads, weights, and I wouldn't relate with speed. Unless there's very heavy seas, and then the speed, of course, then there's a relation between the seas and the speed. But apart from that, okay. It's okay.
From Renato. If there is an alignment of the shaft, is it considered to be wear of equipment, or it can be related to unexpected damage and be able to claim it to the insurance policy?
If there is alignment issue?
If there's a misalignment of the shaft, is it considered to be wear of equipment, or can it be related to an unexpected damage and be able to claim it to the insurance policy?
Yeah, I think all this can be claimed to the insurance to a certain point, because as I explained, the thing is, when we think about alignment, is sometimes we have to think of misalignment or misalign it a little bit so that it gets aligned. So again, I think I said this in the beginning, and if the vessel is resting on blocks, perfectly aligned blocks, and we make the alignment, it's all perfect. When the vessel is afloat and with the thermal rise of the engine, it might be that the hogging and sagging there, it creates misalignments during the operation. So in order to avoid damages, there might be an offset there, and the clearances might be a little bit offset. I mean, they have to be slightly misaligned to compensate all the forces and all the issues that the vessel face during their operation, cargo-wise, sea conditions, and forces applied. So yeah, I think it can be claimed, but alignment is not completely scientific and has to consider a number of factors. Thank you very much for your attention.